Hello everyone, with the grace of God, we begin this presentation. This presentation is part of the concrete solution category. Our team, Green Concrete 1, focuses on sustainable concrete approaches. The main cementitious materials used in this study were slag cement, supplied by Isfahan Cement Company, and Type 2 cement supplied by Ardistan Cement Company. This project was carried out by an 8-member student team working collaboratively with dedication. It was guided under the valuable supervision of our academic advisor. The main problems we aim to address in this study include high cement consumption, which leads to high CO2 emissions, the need to increase concrete durability and strength, and the necessity to reduce costs while improving sustainability. To address the challenges mentioned, we propose the following solutions. First, using slag cement to partially replace Type 2 cement helps reduce CO2 emissions. Second, our approach focuses on long-term durability and sustainability. Third, we utilize industrial byproducts such as slag cement to enhance concrete performance. Finally, these measures contribute to lowering CO2 emissions and promoting a healthy natural cycle. In short, this represents a sustainable approach to high-performance concrete. Slag cement improves concrete performance due to several key properties. First, it generates a lower heat of hydration compared to Type 2 cement, which significantly reduces the risk of thermal cracking during curing. Second, this lower heat helps maintain uniform temperature throughout the structure, ensuring better structural integrity. Finally, slag cement enhances long-term durability by increasing resistance to chemical attack and improving overall sustainability, making the concrete more resilient over time. Isfahan Cement Company is leading a producer of cement in Iran. The company efficiently utilizes industrial byproducts such as slag to produce sustainable cement. The chart here shows the annual production of slag-based materials, highlighting the potential for eco-friendly concrete solutions. The main objectives of our project are as follows. First, to increase the durability and strength of concrete. Second, to reduce cement consumption. Third, to lower production costs. And finally, to improve sustainability and minimize environmental impact. In this study, 3 concrete mix designs were prepared. Mix 1 contains 100 slag cement. Mix 2 contains 50% slag cement and 50% Type 2 cement. The control mix, or reference sample, is made entirely of Type 2 cement. The main materials used in this study include Type 2 cement, coarse aggregate, 10 mm and 20 mm, sand and slag cement. Additionally, water and plasticizer were used during the mixing process. The preparation process for all 3 concrete mix followed 7 steps. First, all raw materials including cement, slag aggregates, sand, water, and plasticizer were carefully weighted to ensure accurate proportions. Next, the dry materials were thoroughly mixed using a concrete mixer. Water and plasticizer were then added to the mixture, making it ready for casting. The workability of the fresh concrete was checked using the slump test. The target slump was approximately 12 cm, ensuring the mixture was suitable for molding. The mixture was poured into cubes, cylinders, and flexural molds. The molds were compacted using a rod and rubber mallet to remove air pockets. Samples were left at laboratory temperature for 24 hours to set. Finally, the specimens were demolded and transferred to a water tank for curing. Here are some images showing the preparation and curing of the concrete samples. You can see the molds before and after applying release oil, the filled and leveled molds, the demolded dry samples, and finally the samples placed in a water tank for curing. After 28 days of curing, mechanical tests were conducted on the concrete samples. These tests included compressive strength, tensile strength, and flexural strength, which help evaluate the performance and durability of the concrete. The results of these tests will be presented in the next slide. These results present the 28-day mechanical test outcomes for the 3 concrete mixes. In terms of compressive strength, Mix 1 containing 100 slag cement showed better performance compared to Mix 2 and the control mix. For tensile strength, although the slag-based mix exhibited slightly lower values than the control sample, all results remain within the acceptable range of C30 concrete, which was the target strength class of this study. Overall, the findings indicate that the use of the slag cement can contribute to improving the overall performance of concrete and can be considered a suitable and sustainable alternative to conventional cement. The slide shows the failed concrete specimens after mechanical testing. Images of compressive and flexural test samples are presented for all 3 mixes, including the control mix and the slag cement-based mixes. The failure patterns provide a visual comparison of the behavior of different concrete mixes under loading. In this study, 2 slag cement concrete mix designs were investigated and compared with a control mix. Mechanical performance, workability, and durability aspects were evaluated. The results demonstrate the potential of slag cement as a sustainable and effective material for concrete production. Thank you for your attention, and a special thanks to the jury members for their valuable time.